Okay, so we've talked about configuring segments. We've talked about segment profiles. We've talked about what these segments even are and how this all comes together. Now, here we're going to talk about what's going on as we forward these packets around the around the NSX infrastructure. What happens as we talk from hypervisor to hypervisor, from tunnel endpoint to tunnel endpoint? That's really what this is all about. But to get to the packet flow, we've got a whole bunch of little stuff that we have to figure out, that we have to understand as far as the runtime for our logical switching before we get there. So let's dive in. So we have these different runtime tables that we have to maintain. We have to keep up with. We have to fill out in order for all of this to work. Well, why? Well, the tunnel endpoint table tells us which tunnel endpoints could be valid targets for our traffic for any given segment. The MAC address table tells us for a given MAC address, for a given destination virtual machine, what tunnel endpoint is servicing that VM. Where do I need to forward the frame to get to that virtual machine? And then we have an ARP table. The ARP table is great. The ARP table allows us to minimize the amount of actual ARP traffic out on your network because, well, if we've got the ARP mappings, why don't we answer that locally? Why don't we answer that ARP query locally rather than just flood that around our network? That makes a lot of sense. So that's what we've got going on here. We've got these three tables that we're going to show you how NSX builds. And we're going to start with the tunnel endpoint table because that's the first one that's going to kind of come together. This has to come together first so that we can continue on with everything else. And so when I have a segment and that segment doesn't have any workloads on it, there's nothing on a given hypervisor, we don't have a tunnel endpoint table for that hypervisor. But when I power on a virtual machine, so here we've got next to VMs 1, 2, and 3. We've powered these virtual machines on. We turned them right on. Now I have a workload on VNI 73728. All three of these transport nodes kind of perk up and they start to build out a tunnel endpoint table for that specific VNI, for VNI 73728. And they're going to sit here and they're going to program in. They're going to say, you know what? I have a workload on VNI 73728. So ESXi-A says, well, I have, my tunnel endpoint is in VNI 73728. Well, ESXi-B says the same thing. Well, TEP B here is in VNI 73728. TEP C does the same thing, right? So I have a tunnel endpoint on each of these hypervisors servicing a workload attached to VNI 73728. Well, this is great, but don't you think it might be helpful if these workloads knew that all three of these tunnel endpoints were servicing workloads on this VNI, on this segment? I think so. So we're going to take these tunnel endpoint tables, these small little tunnel endpoint tables, and we're going to send an update to the central control plane. All right, each transport node, now that it has updated its local tunnel endpoint table, each transport node is going to send that data to the central control plane. What's the central control plane going to do with it? Well, it's going to curate all of that information. It's going to say, okay, I've received a TEP report from ESXi-A and ESXi-B and ESXi-C, and they've all told me that they have a tunnel endpoint servicing stuff on VNI 73728. So let me set up my central control plane tunnel endpoint table for 73728 and show that I have all three of these tunnel endpoints servicing workloads here. Well, that's great, but it only does me so much good to have this data centralized. So what's the central control plane going to do now? Well, central control plane is going to evaluate that all of these TEPs belong to different transport nodes. And so we're going to publish this tunnel endpoint table to all of the transport nodes in that TEP table, so that each hypervisor now says, oh, look, I have a tunnel endpoint A and a tunnel endpoint B and a tunnel endpoint C that are all servicing workloads on VNI 73728. Right? So now all of my hypervisors know about all of the other tunnel endpoints. Right? All of my TEPs know about all the other TEPs that they need to know about right now, which is great. Now we can start moving traffic between tunnel endpoints. But how do we know what traffic to move to what tunnel endpoint? Well, that's where the MAC address table comes in. So the MAC address table, right, just like the tunnel endpoint table, when I power on a virtual machine, we're very early on going to realize that there's a MAC address attached to that segment. And so we're going to build a MAC address table. And that MAC address table is going to say on VNI 73728, I have MAC address 1 or MAC address 2 or MAC address 3, depending on the host I'm looking at. But I have a MAC address serviced by my local tunnel endpoint. Right, and that's the difference between our MAC table in NSX and, say, a MAC address table on a physical switch. Right, a MAC address table on a physical switch is going to say this MAC address for this VLAN for this MAC address, we have to forward the packet to this switch port, or forward the frame through this switch port to get it where it's going. Well, here, our MAC address table says on this VNI, to get to this MAC address, we need to forward that frame to this tunnel endpoint. Again, as we're powering these virtual machines on, the MAC address table is pretty slim, right? There's not much in it because we've only got the local entry. Well, what are we going to do to fix that? We're going to do the same thing we did with the MAC or with the tunnel endpoint table. We're going to send a MAC address table update to the central control plane. Okay? So the central control plane, just like with the TEP table, it's going to curate all of that information. So we're going to take this information, build one large central MAC address table. So now the central control plane says, if we want to forward a frame to MAC address 3, we need to forward that to tunnel endpoint 3. All right. Great to know. But again, like the TEP table, only so useful at the central control plane. So what are we going to do? We're going to publish that to all of the transport nodes servicing VNI 73728. So now everybody knows. So now if virtual machine 1 wants to talk to virtual machine 3, when that frame gets out to the virtual switch, out to the tunnel endpoint to say, I need to go to MAC address 3, we can now look up locally and say, well, MAC address 3 is serviced by tunnel endpoint 3. So let me send a Geneve packet with this frame over to tunnel endpoint 3. So there's our TEP table. There's our MAC address table. Now, we also maintain an ARP table. We've got some of the information from the ARP table already. We've already got MAC addresses. We already know what tunnel endpoints service what MAC addresses. That's great. Why do we need an ARP table? Well, we need an ARP table primarily so that we can suppress ARP requests. If we think about our networks, a whole lot of the traffic out on our networks is ARP traffic. It's broadcast traffic because I've got this machine ARPing for that MAC address and this other virtual machine ARPing for another MAC address and so on and so forth. And ARP is very much a broadcast because it's trying to make the mapping, right? Provide the mapping for, an IP address to a MAC address, because when it comes down to it in my network, the MAC address is where I'm forwarding a frame, right? The IP address, that becomes secondary. So we need to know the MAC address for a given IP address. ARP request simply asks that question. Who has this IP address? And we wait for a response. We broadcast that. Well, that's a lot of traffic on our networks, right? Systems use a lot of ARP. So we want to minimize that. And by maintaining an ARP table for our overlay segments, at least within the context of NSX, we can minimize that ARP traffic and answer those requests locally, right? Which is great. So what happens here? Well, when a virtual machine powers on, right after we initialize the network adapter and initialize the TCP/IP stack in the operating system, we're going to have an IP address mapping very quickly, right? Whether we're getting it from DHCP, we can snoop for DHCP. We saw that in the IP discovery profile, right? That's what's doing this work, is that IP discovery segment profile. So, we can watch DHCP traffic and see what the DHCP server assigns to this MAC address. That's great. That's one way for us to get that mapping. How about an ARP request? An ARP request, if I've got a static IP address, that'll pretty quickly tell me. VMware Tools, well, VMware Tools just knows, right? The minute VMware Tools initializes, we can get the MAC address and IP address and make that mapping, put that information all together, tell NSX about it. So when this virtual machine powers on, right? So step one of all three of these workflows is essentially powering on the virtual machine the first time on this segment. And we're going to collect that mapping, that MAC to IP address mapping to populate the ARP table. And so each of these hypervisors is going to have an ARP table for VNI 73728 that's going to say, on VNI 73728, I have MAC address 1, which maps to IP address 1. Well, just like the tunnel endpoint table and the ARP table, or the MAC table rather, we're talking about the ARP table right now. Just like the TEP and the MAC table, we're going to report this information, this update, over to the central control plane. The central control plane is then going to curate this ARP table. And what are we going to do? You may have guessed a pattern by now. We're going to publish that ARP table to all of the transport nodes for VNI 73728 here. So that when VM1 wants to talk to VM3, I used this example a couple of minutes ago. When VM1 wants to talk to VM3, well, VM1 is going to send out an ARP request, right? The operating system is going to send out an ARP request that says, who has IP3? Well, at this point, ESXi1 can answer that, right? It can look at that local ARP table and without flooding that ARP request, can craft a response that says IP3 belongs to MAC address 3. At that point, we can start sending a packet. Now here we're sending VM1 to VM2, right? So my example of VM1 to 3, start substituting VM2 for VM3 here. It's okay. So VM1 sends out its ARP request to VM2. We resolve that ARP request, probably through the ARP table. And VM1 is then going to send out an Ethernet frame destined for MAC address 2. That frame is going to get to our virtual switch. The virtual switch is going to look at the source MAC address, just like any other switch does, validate that it's coming in on the right port, and then it's going to look to the destination. Well, here we're going to look at the destination MAC address and look that up in the MAC address table on the local control plane. So that we can then say, all right, if I want to get to MAC address 2, I have to forward this frame to tunnel endpoint 2. Well, since that's an external tunnel endpoint, we now need to encapsulate that Ethernet frame in a Geneve packet. And we're going to send that Geneve packet over the physical network, right? Over across our overlay network, our transport network, to get to the destination tunnel endpoint. Well, we get to the destination tunnel endpoint, the ESXi2 or ESXi-B rather tunnel endpoint decapsulates that frame, right? It starts stripping off all of those headers. It gets to the Geneve header. It says, okay, this frame needs to go to VNI 73728. I can work with that here. I have that programmed. I have workloads. So we'll go ahead and take that layer 2 frame and put it on the virtual switch. The virtual switch is then going to look at the destination MAC address and say, well, that destination MAC address is over here on this switch port. Let me go ahead and forward that along to the virtual machine. All right, the destination virtual machine will receive that frame and off we go. Right? That's how a packet flows, or a frame more precisely flows through a Geneve overlay network. All right. Now, That's for unicast traffic. What happens when I don't have unicast traffic? What happens when I have a broadcast that needs to be sent? Or how about an unknown unicast frame or a multicast frame? Three different types of traffic that we are by default simply going to flood across our logical switch. What happens when we get those different types of traffic from a virtual machine, right? A virtual machine sends a broadcast frame, or it sends a multi or a unicast frame that we don't have an entry for in our MAC table, or we sends a multicast frame, whatever it might be. How are we going to deal with that? Well, we've got two different ways we can deal with that. These are called our replication modes. We have a hierarchical 2-tier replication mode. This is our default. This is what we're going to use most of the time. And then we have head-end replication, which is non-default, and we're probably not going to use in too many cases. So how do these work? Well, head-end replication, let's look at the non-default first. Here we've got a scenario, right? I've got 3 different layer 2 domains. Maybe my 9 hypervisors here are servers in 3 different racks in a layer 3 spine leaf fabric, right? So that rack A, my green rack, and rack B, my blue rack, and rack C, my orange rack, are all different layer 2 domains. That's not an uncommon type of scenario. Well, I've got a virtual machine on transport node 1 that sends a broadcast. And if we look at the tunnel endpoint table and we look at all of the different tunnel endpoints and transport nodes that are included in that tunnel endpoint table, we see that everything except transport node 6 is included, right? Transport node 6 doesn't have the VNI. It doesn't have a workload on VNI 73728, so we don't have to worry about that. Well, with head-end replication, we're going to look at that tunnel endpoint table, and transport node 1, where the broadcast is being sourced, transport node 1 is going to make lots of copies of that frame and send 1 frame to each possible destination tunnel endpoint. When that frame gets there, when that Geneve packet gets there, we're going to open that up and see that it's a broadcast and flood that to the local host switch. So that's what we're doing with head replication. Now, that places all of the burden on replication on the source hypervisor and sends a whole lot of packets all around the network from one spot. That may or may not be desirable. Now, with 2-tier replication, with our default behavior, if we have this scenario, we're going to add one more thing when we receive the tunnel endpoint table, right? When transport node 1 receives its tunnel endpoint table, it says, oh, well, I've got transport nodes 2 and 3 and 4 and 5 and 7, 8, and 9 in my transport node table. We're going to look at subnets, and we're going to group transport nodes into local and different remote broadcast domains or subnets. And so what we're going to do is transport node 1 is local as far as the TEP subnet to transport nodes 2 and 3. Transport node 1 will simply create a copy of the broadcast frame and send it to transport node 2 and send a copy to transport node 3 so that everybody in the green layer 2 domain gets a copy of this frame to be broadcast. Now, when we received the tunnel endpoint table, we identified the transport nodes in the blue subnet, and we identified the transport nodes in the orange subnet. And in each of those groups, transport node 1 chose a proxy tunnel endpoint, or an MTEP, to be used in cases exactly like this. Now, any tunnel endpoint at all can behave and will behave as a proxy tunnel endpoint. They don't even have to know that they're chosen as a proxy. So in this case, transport node 5 and transport node 7, they were chosen as proxy tunnel endpoints. They don't know, right? Nothing in NSX tells these tunnel endpoints that they've been chosen as MTEPs. But what transport node 1 does is it'll create a Geneve packet to send to transport node 1 and transport node 7, its proxies. And it'll have a Geneve option set, one of those variable length options that we saw. It'll have a Geneve option set that says, replicate this, please. And so when transport node 5 receives a copy of that Geneve packet and it starts processing the Geneve header, it sees that flag that says, please replicate. And it goes ahead and it sends a copy of that frame to its local virtual switch and it creates an additional Geneve encapsulated copy and sends to each of its local tunnel endpoints. In this case, transport node 5 is responsible for sending a copy of that Geneve packet to transport node 4 so that transport node 4 can flood that to its local host switch. Transport node 7 creates a copy and sends it to TN8 and 9 so that they all get a copy. In other words, we're distributing that replication workload. Instead of transport node 1 being responsible for creating packet upon packet upon packet upon packet, we're saying transport node 1 is responsible for things in its subnet, transport node 5 is responsible for things in its subnet, transport node 7 is responsible for transport nodes in its subnet. So we're distributing the workload, which is great. Any transport node, any tunnel endpoint more precisely, can be and will be a proxy. It just has to receive a Geneve packet that has that replicate locally flag configured. And every transport node is going to choose its own proxies, right? That's done when the transport node receives the latest tunnel endpoint table from the central control plane. So now we're going to take all of this information, we're going to put it to good use. We're going to configure up some segments. We're going to prepare. We're going to build segments. We're going to build a web segment, an app segment, a database segment. If you're feeling really excited, you can go and see that you can change the replication mode on a segment. There's nothing official in the lab. That would just be exploratory time that you're taking advantage of in the lab. But we're gonna attach some virtual machines to these segments. We're gonna look at the network topology that we talked about and kind of see. We're gonna review that network topology a little bit as we continue building things out, just to see all of the new objects that come in, and then we're going to test. We're going to make sure that this works. Now, we're really only going to have multiple workloads on the web segment. So we're just going to kind of do that and check those, but we're going to make sure that our segments work and that our transport networks are functioning and our overlays are doing what they're supposed to do. So go jump into Lab 5. Come back when you're done with that. We'll go ahead and wrap up all of this segment talk. All right? See you guys in a few minutes. All right, we've got our segments now. Everything's in good shape there. Everything should be pretty happy. It should be working. We should be able to ping from Web 1 to Web 2 and so on. That should be fine. So we talked in this specific video about packet forwarding and ARP tables and MAC tables and tunnel endpoint tables, how the control plane's functioning and things that the control plane's keeping track of. And we kind of talked about ARP suppression and packet flow, right? All that good stuff. Now, in the bigger picture, in this series of videos, what have we covered? We've talked about how a segment or a logical switch, more precisely, is a representation of the layer 2 broadcast domain. And a segment includes that logical switch plus additional configuration stuff, right? VPN or router interfaces or things like that. We talked about how each segment has its own VNI, and the tunnel endpoints are what actually move the Geneve data from transport node to transport node and all kinds of stuff, right? We've covered a lot of ground here. So we're not done, though. We are most definitely not done. We've got a lot of good stuff under our belt at this point. More excitement is coming. We've got logical routing on deck in the next series of videos. I can't wait to see you there.